All right, so I'll just sort of continue here. detritalPy runs through Python, and to use it, you have to use something called a Jupyter Notebook. And I'll explain a little bit more about what these are later in the course. And I should mention that most of the plotting functions use this library called matplotlib. So what can detritalPy do? It can do a number of things. The only function that we're going to explore today is plotting detrital age distributions. So following right along with what Kurt was just saying. So you'll see a plot here that displays 8 samples, both as a cumulative distribution on the top, a relative distribution on the bottom, a histogram, a pie diagram. There's all these different ways of plotting, displaying these types of data. The course is going to be trying to explore these different options. And then at the end, you will apply what you've learned on a couple of real world data sets. detritalPy can do some other things that we're not going to cover. So if you have rim and core ages, it can plot those. If you have some geochemical data, you can plot that along with your age distributions. You can look at the various age fractions. So if you want to divide up your geologic time into different time periods, you can look at the proportion of ages in each of those buckets. There's some very basic mapping features. Kurt mentioned maximum depositional age very briefly. There are some functions for that. We'll cover multi-dimensional scaling later on the plot or in the course. And then there's a feature if you collect both crystallization and cooling age data, there's a function for that. So to use detritalPy, it requires data to be formatted in a fairly specific way. And there's a reason for this, which I'll explain at the end of the course. But basically, you need an Excel file with 2 worksheets. And by worksheets, I mean these little tabs at the bottom. You need a samples worksheet, which has a row for each sample. And then you need a data worksheet that has a row for each analysis. And the key thing is that the sample table and the data table have to be linked with a sample ID that's the same. So if you have a particular sample name here, it's got to match over here exactly. Now you can put a lot of different data in these. You can put the age and the basin, coordinates, what source it comes from. In the data table, there's all sorts of different things you could do. But in general, if you just want to plot data, you just need to have the age and uncertainty. So that, and there are some default column headings. It doesn't matter where these columns fall in these sheets. They can be in any order. All right, so today we're going to experiment with this plot all function. And I'm first going to walk you through all the different options. And a lot of this is going to follow directly on what Kurt just presented. And then at the end, we're going to explore 2 data sets if time's permitting. The first is from the Bengal fan, published by Mike Bloom and co-authors a couple years ago. It's an open access paper. And then there's another data set by George Garrels that just came out. And if we have time, we'll explore that one as well. So you should be making your own plots. You should be trying to customize them with the options that we've gone over. And as Kurt mentioned, there's all sorts of different ways that you can display this data. And both of these data sets have some distinct challenges. So if you feel comfortable, you can share your plot with the group by visiting this Google presentation file. And the link to this is also in your step-by-step guide. So feel free to share. You don't have to, but it would be fun at the end to sort of see what everyone comes up with. Okay, so how do you actually run detritalPy? The way I've always done it is you have to have Python installed on your computer, and then you go and you download detritalPy, and you sort of load the Jupyter Notebook, and you're off to the races. However, this requires you to have Python installed and make sure all your ducks are in a row. And sometimes, particularly if you're new to Python, this can be a bit of a process. And I'm happy to help anyone who needs help with that. But for this course, we're going to run things through Google Collaboratory. Google Collaboratory basically runs Python in your browser, and you don't have to have it installed. So all you have to do is click this link, and it should take you to the notebook, and we will explore from there. But if detritalPy is something you actually want to use in your own research, I might suggest that you go with this option 2, and there are detailed instructions for this. Just given the time constraints, if you try to do option 2, I'm not sure I'll be able to help you troubleshoot real time today, but hopefully I'd be happy to help you sort of after the short course with getting that up and running. Okay, so with that, I will drag over the step-by-step guide. So you should all have a copy of this. And if you go down to the detritalPy application part, there's a link here, this Google Colab notebook link. So at this point, feel free to go ahead and click that link, and it should take you to this page. So I'll give everyone a moment to sort of find that link. Again, it's in your step-by-step guide, and go ahead and click it. I should mention that sometimes when I've clicked the link, it will have a hard time loading it, and it'll ask you to refresh it. If that happens, just simply come up here and reload it, and usually it works the second or sometimes the third time. I've noticed that GitHub is a little, can have some problems, including maybe this time. There we go. See, it sometimes brings it up, sometimes doesn't. I'm not sure why it does that behavior, but if you get to this screen, stop, because that's where you sort of need to go from here. Maybe can we find out from the audience, sort of anyone who needs a bit more time to get through the step? Can't see the chat bar. You think
nobody's indicated that they need additional time.
Okay. Well, we'll continue then. The instructions are also in the step-by-step guide. So if you are behind, you can follow the instructions to catch up. So basically, the next step is open in Colab. And I should mention that to do this, you need a Google account. So if you don't have a Google account, you'll be kind of out of luck. You can still follow along with what I'm doing, but to run Google Colab, you do need an account. So if you've clicked on that link and you're not signed in, it will prompt you to sign in. You can see I'm already signed in, so that's fine. Okay, so here's the notebook. The notebook is kind of a nice way of working with code because it includes cells. So here's a cell, and here's a cell, and there's a cell. And cells can either have text or they can have code. So what's nice about notebooks is you can have some text that explains the code, and you can kind of work from top to bottom, running each cell individually. So here's the first cell with code. It's this big cell here. And you'll notice that there's a little arrow here off to the left. So you can run that cell by clicking that. It'll warn you, it'll say this was not authored by Google. Only run this if you trust it. You'll have to trust me and click run anyway, which in case it will start to do things. So what it's doing here is it's going in and installing the various libraries that you need to run detritalPy. This is kind of nice because that means you don't have to install them. Google does it for you. At the end of that cell, there will be a link, and you have to click on that link, and it'll say, go ahead and choose your account. It'll say allow, so go ahead and click the allow button, and then it will give you a code. So go ahead and copy that code by hitting this little button there. Go back here and just simply copy paste into your verification code and hit enter. So I'm not exactly sure why you have to do that, but it's some sort of verification step to make sure that you have a Google account and that you are who you say you are. All right, so has everyone gotten that to work, or is there anyone that's struggling with that step? Okay, I'll
Where do I find the code?
sorry.
Where do I find the code?
So there's a link right beneath or above the box that says the box to paste the code. There's a link. So if you click that link, it will take you to a page. It'll ask you to sign in, authorize, and then it'll give you a code. I'm not sure if I can do it again. Let me try to do it again. So again, hit that. Yeah, because I'm already logged in, when I re-hit it, it's not showing me again. But when you scroll to the bottom of this box, there's a link and there's a box to paste your code. Go ahead and click the link. Any other questions or trouble with this step? Okay, I'll go ahead and move on. If again you have questions, there is a step-by-step guide. If you do get behind, I've tried to list out all the steps, and so feel free to follow along there. All right, so now we get to the part of the notebook where you actually run the code. And if you haven't used Python before, this might seem a little unfamiliar to you, but you really don't have to do any coding. The code is sort of buried in these functions. All you have to do is run the cells and change the parameters. So here's the first cell, or the first step is to import the required modules. So just go ahead and click that, and it will import everything. It'll tell you the detritalPy version that you're using. This is the most up-to-date one, so that's good. Second step is to import the data set. Click that, it will import the data. Now, these two files were actually loaded up here. These are linked with my Google Drive account. So Google is pulling these files from Google Drive. So if you wanted to load your own data, you'd have to get the file ID that goes along with your file, and you could reproduce this code. But for this example, we're just going to use the example data set. So go ahead and load the data. And then to see what you get, you can basically press this code. So here's what the data set looks like. There's a sample ID, there's some information, the point of rock sandstone, coordinates. When you get over to this side, there are all these data points that relate to the zircon analyses themselves. And note that these are single values, but when you get over here, they're actually a list of values. And that's because this sample has multiple analyses, as most samples do. So that's just the way that the data is structured into detritalPy. You don't have to worry about that too much, but just so you know. So to select samples, you key them to their sample ID. So there's a couple ways to do this. So the easiest way is just to take the sample names and put them in a list like this. So if you do that, it'll load those samples, and then click that cell, and it will basically tell you how many analyses in your first sample. So there's 100. So you want to do this if you want to plot samples sample by sample, like how Kurt was showing. But if you want to plot samples in groups, you can do that too, and you use this what's called a tuple structure. So to do this, you basically put the samples you want in brackets, and then with everything within parentheses with the name of what it is to the right. You can just sort of follow this format. So what I'm doing here is I'm combining 3 samples into the point of rocks and 5 samples as a Butano sandstone. And these are different formations, and that's why I'm grouping them this way. I'm trying to group these data by formations. And so I can run that, and if I run this cell, it'll say the first sample group has 298 analyses. So there's 3 samples, they each have about 100. You add them together, now you have 298. Okay, so these first 2 steps were basically to review, importing the required modules, you just have to do this once. Importing the data set, you only have to do this once unless you change your data set, and then you'll have to re-import it if you do. And then you can, the third step is to select the samples that you want to plot. All right, so now we'll get into sort of the nuts and bolts of actually plotting these detrital age distributions. So here's a function that basically just takes the samples that you've done and it just plots them with all default settings. So what you're seeing here is, I believe, a kernel, a KDE with a sort of set bandwidth. It's showing you both a cumulative distribution, so again, probability from 0 to 1 on the top, and the KDEs on the bottom here. So that's the default way, but you can control how these plots look like. And so what I'm going to show you all these different options, and then at the end, I'm going to see if you guys can tweak these options to come up with plots that you think look good for your data set or for the example data set. So there's a what to plot option. So if what to plot equals relative, then we drop the KDE and we only have we drop the CDF, we only have the KDEs. What to plot is cumulative, then we only have the cumulative. If what to plot is both, well, that's kind of self-explanatory. It will give you both. I should mention, detritalPy will give you, if it's a sample group, it will give you the number of samples in that group, the number of grains being displayed on the plot, and the total number of grains in that sample group. So if you're only looking at a subset of your data, you can sort of get all that information right there. So most of the data is on the young side. So what if we want to change the x-axis? Well, you can do that with this x1 and x2. These two variables here. So now I've said the left side of the plot 0, the right side of the plot is 300 million years. So now we've zoomed in on just those two. Okay, so now we're going to get into some of the nuts and bolts of sort of how you can plot data. So there's two ways of plotting age distributions. The first is to, and you control this with this separate subplots function. So if separate subplots is set to false, like it is here, then you make a plot that is analogous to those nice plots that Kurt showed from the LaserCon Center, where all the samples are just stacked on top of each other. And where one sample ends, the next sample begins. And so you can see that there. But if you set that to false, each sample, oh, sorry, that should be set to true. Each sample will fill its own box. So again, these are subplots. If you want to separate them, you can. And if you don't want to, if you put this to false, you basically make a plot that looks like the LaserCon Center plots. Now, Kurt mentioned something about normalization. So that's where you take the curve and you sum up all the Gaussian distributions, and then you normalize it so the area under that curve is equal to 1. Now, if separate subplots is false, it's always normalized. So that's why this is taller than this one, because the peak is higher, and the area under these curves is the same. But you don't actually have to do that in detritalPy if you don't want. So if you put separate subplot is true and norm plots is false, these are now no longer normalized. Each plot will fill the subplot box. Now you might wonder, well, which is better? And I'll say it's kind of, I'm not here to tell you sort of the right way to do it. I'm just here to show you all the different options and sort of let you make the choice. So if I put norm plot is true, then you can see that they're normalized again. But if norm plot is true and separate subplots is false, or is also true, then this one won't fill the entire subplot because it's normalized to the other one. So those are the two general sort of ways of doing that. Any questions before I move on at this point? I hear silence, so I will continue. All right, so there are some other things we can do. So some people like to plot the x-axis as a log plot instead of being a linear scale. You can do that with this plot log. I don't personally often do that, but if you have a situation where you have a lot of really young grains and that are high precision, a lot of old grains that are lower precision, this is one way of sort of trying to display the data in that way. There are also parameters that allow you to adjust the size of the plot, and these are these plot dimension parameters. So right now, I've made the plot a little bit skinnier with this W. If I prefer a fat plot, I can make that 10, and it'll be sort of wide. The CDF, if I find that kind of tall, I can make it shorter, and so on. So you can basically tweak the plot dimensions to get it like you want it to be. Okay, now to get into some of the fun stuff. So Kurt talked about PDPs, KDEs, CDFs, histograms. The detritalPy allows you to plot all of these, and you can basically just sort of it allows you to make the plot like you want to do. So I'll first talk about plotting PDPs and KDEs. So if plot KDE is true, it will plot the KDE. So that's what's shown right here. And you'll see the bandwidth is optimized fixed. This is one of the automatic or the algorithms that selects the bandwidth for you. And if you're interested in this more, I put a paper in the literature folder that you should have access to on Drive that goes into this a bit more. And I believe it's discussed up here. So there's the link to that paper if you want to learn more about that. But we can also put this as a number. So we could say, let's use say a 5 million year bandwidth. I think there was a question earlier about how you set this. You can basically set the bandwidth to be whatever you want. And you can see how it gets spiky or smooth. Now, if you don't want to plot a KDE, set that to false. If you want to plot a PDE or PDP, set that to true, and it will plot the PDP. If you want to plot both of them, oh, sorry, question.
Yeah, we had a question whether or not you can annotate these plots, for example, like with the age of the peaks. Or
Yeah, we'll get to that. There is a peak age annotation that I'll show in a short bit.
Okay,
yeah.
Excellent. Thank you.
So you can also plot them together. So I'm going to plot both the KDE and the PDP. I'm not going to color them, and I'll make the KDE super smooth so you can see the difference. So here the KDE is super smooth. The PDP is kind of spiky because it uses the actual data. And you can see from the histogram that this KDE is way over smooth. So the histogram shows that in this case, the PDP is following that better. So if you see that, you might want to, use a more realistic KDE bandwidth. Here they almost overlap exactly. So there they agree quite well. So Kurt mentioned cumulative distributions, and detritalPy can plot those as well. So there's a couple of options. In fact, I'm going to make C, I believe C is the height of it. So let's make this 5 and see how that looks. Okay, so I'm just going to plot the type of CDF that Kurt mentioned. So basically, the x-axis is discretized, and each time you have an age, the CDF will tick up. Now it's not a true CDF like the one that Kurt showed, where the lines are vertical, because detritalPy works with a discretized x-axis. But if the default discretization level is 1 million years, and so it's sort of a close approximation for a true CDF. But you can also plot the cumulative PDP. So here's the cumulative PDP, and it's the same exact idea, but now it's smoothed. So Kurt mentioned that the CDF doesn't incorporate uncertainty. If you want it to, you can use the cumulative PDP, which then does incorporate that. And of course, you can do the same thing with the KDE. Just some other things that are fun. If you want to actually see your data points, there's this plot ages on CDF function, and you can actually see the data points plus their error. And I've just thrown them on the CDF in case you want to actually see the data points. detritalPy gives you some different options for coloring. And so I'm going to show this real quick. So you can color, if you set color PDP to true, it will basically color according to set colors. But if you use this color PDP by age, you can basically define age ranges and associated colors. So in this case, 0 to 23 MA is slate gray, 23 to 65 MA, royal blue, etc. So here I basically defined a list, defined age brackets and colors, and then you can basically fill in beneath the KDE or PDP with that color. I personally like to look at these plots, but it sort of depends on your taste and sort of how you want to do things. If you have these colors defined, you can also plot a pie chart, which is another way that sometimes people display these data, particularly when you're trying to display them on a map. So if you have a map, you can't, it's hard to put, you know, it's hard to show a CDF or a PDP, but usually you can get some good information across if you choose appropriate colors and age categories. And so you can see the pie there. And the pies are really good for proportionality information. So here you can see that the purple wedge of the pie is really big. It's about 50%. And over here, it's probably about 10 or 15%. And you can sort of see that in the size of that purple, those purple ages. Any questions?
Glenn, we did have a question about how to go from the smooth sort of cumulative PDP or KDE to the CDF step function. So maybe can you run back to that and demonstrate that again?
So it's just through these variables. So if you set plot CDF to true, it'll plot that. Plot PDP to true, it'll plot that. And in fact, you can plot both of them if you want. Now they mostly overlap, but if you look closely, you can tell that they're sort of sitting on top of each other. So you can sort of toggle things on and off with these true false variables. So it's just through setting these variables.
So they're the CDF, the plot CDF plots the step function, the plot CPDP plots the cumulative PDP, and the plot CKDE plots the cumulative KDE. So if you want that spiky sort of step function, set that variable to true, as he's doing now, and the others to false, right? There you go.
Yeah, exactly. And in Python, if you put a number sign, that's a comment. And so these are all comments that basically tell you what they remind you what these variables do. So you don't have to memorize them, just read the comment, and that will help sort of figure things out. Although in this case, I didn't include the comments, but I normally try to. So if you have colors defined, well, I should mention that there's actually, let's see, I changed the what to plot equals relative. Okay, so there's two ways to define these bins. The first one was continuous, right? You define the start and end in a continuous series. Some people prefer to have gaps, and so if you're someone who wants to basically have age ranges with gaps in them, you can use this format, which basically puts each of the age ranges in a list within a big list, and then for each list in the list, you give it the color. So 40 to 50 gets royal blue, 65 to 80 gets gold, et cetera, et cetera. But if you do this, you need to be aware that the pie diagram will reflect that. So the pie will not include ages that are not in your list here. So just be aware of that. And I think Kurt showed one of these plots in his example from Tibet. Some people like to show key ages by these vertical bars, and you can do that by setting plot color bar to true. Again, you have to have your colors defined to do that. And if the colors are too saturated, you can actually use this agebend alpha term to set transparency. So that's a little bit less, less saturated. And if you prefer to set the transparency for each bin, you can make this a list instead of a number. So this is 50% transparency applied to everything. This is variable transparency applied. And these just have to match up with the age bins you've defined up here. So in this case, I've made it increasingly saturated as you get older. But of course, you can choose these according to your personal tastes. Something that I've never seen anyone do, but I added it, is to plot age distributions as heat maps. So what's shown here is basically the heat map reflects, it just scales to the probability distribution, whether PDP or KDE. In this case, I'm showing a KDE, but you can actually show that the heat map, it gives a different way of visualizing the probability. So you can see that the Jurassic here has high probability. Here, it's got a little bit of a dip there, but a bit less. And you can see the Cretaceous. They don't exactly line up, but they're pretty close. So I'll leave it up to you if you think this is a good idea. You can change the heat map type. There's all sorts of different heat maps that are available, and you can go to this link to get your list of heat maps. So you just basically can change that. Okay. Someone asked about peak ages, and you can do that. There's a plot peak age function, and I give some information up here, and this actually uses the peak utils library. So if you want to get into this, I would recommend looking at that library. There's a number of different parameters that you can use to control what you count as a peak. For example, there's this threshold here, and if I set this threshold to be really high, let's see if this actually does anything. It will only count peaks that are sort of that size. But if I use a really low threshold, it will count everything. And there's some other things, some other parameters that you can do to sort of control that. But you have some power through this peak utils library to sort of control what you think is a peak. And now that's a little bit, there's some subjectivity in that for sure. But this can also export a CSV that will give you the peaks and tell you the number of grains in those peaks that overlap with uncertainty. And so that's useful if you want to, only use peaks that have a certain number of grains. You can get that through that exported CSV file. All right, I'll just keep going through here. I had a user come to me and ask about using a split axis. So sometimes it's advantageous to split your axis such that the X scale changes. And again, this is sort of a choice that you could make, but if you want to do this in detritalPy, you can. So the way you do that is the X1 and X2 variables that control the X-axis plotting ranges, if you make them a list like this, it will then split the axis. So this would be, the first part would be 0 to 300. The second part would be 300 to 2000. And then down here in the width, you then have to specify the width. And it's a little bit of a quirk, but the first number always has to be 1 because that's where you plot the pies. So make that one 1, and then the other two can control the width. So let's say I want the left one to be sort of not as wide and the narrow one to be, or the right one to be a little bit wider. You can do that. I should mention that the detritalPy, when it splits the axis, it also adjusts the y-axis scale. So for example, if you compress the relative scale on the right by a factor of 2, it will increase the height of the age distributions by a factor of 2. And that is an attempt to sort of honor the sort of sum to one underneath the curves. I see a hand is raised.
Hi, yeah, I just had a quick question. In this program, can you do something where you have, so let's say you want to zoom in from like 0 to 300 million years, but then on the right, you want to show the entire age distribution. Can you do that, or does it not allow you to repeat values on the x-axis?
I think it can. Find out. No, sorry. Looks like there's an issue there. But why would there be an issue? I'll have to, that's not something I ever tried to do. So I guess not. But I'll have to look into that error and try to figure out why you can't. And if it's something trivial, then I could perhaps do that. But it might be that the code is yeah, I'll have to think about that more. Good comment.
All right, thank you so much.
Mm-hmm.
I guess real quick, what I might suggest is you could run one of these plotting all functions twice and change the upper and lower limits of the axes that Glenn is defining there, and then just put those side by side outside of Python too.
Yeah, you can always do some post editing in Illustrator or whatever software of your choice. And I'll note that the age is sort of squashed against the x-axis. It does not do that in the non-Google Colab version, and I don't know why. So apologies for that, but I didn't try to troubleshoot that. All right, so unless there's more questions, I'll keep going. I want to make sure there's at least some time to work on this yourself. It probably won't be a lot of time, but we're almost done here. But are there any questions?
There's a question about saving, Glenn.
Yes. Yes, I'll show you how to do that in Google Colab during your exercise, so you can save your files. I usually save as a PDF, so it has all the vector preserved. You can save it as a PNG or sort of JPEG or whatever you want. Okay, I'll continue moving on. So sometimes it's good to filter ages. So let's say I only want to look at my old ages. Most of the ages are less than 300, but I can basically filter the data set with these 2 lines of code. And you'll see I'm saying analyses, DF, best age, greater than 300. So that's the data table, and that's the column that we're filtering on, and that's the filter criteria. So if we do that, we then have to reselect the samples because we've changed the data set, and then we can plot it again. So here's what it looks like with all the options stacked on top of each other. I was showing you things piecemeal to avoid sort of option shock, but here's all the options sort of on top of each other. And because we filtered out all the ages that are less than 300, it's only plotting the old ages. So you have that level of control if you want to explore your data. Okay, so we have about 15 minutes left, and what I'd like you to do is go ahead and try this yourself with this data set from the Bengal fan. So the first thing you'll do is download the file, load it. There's a little function for plotting the distribution of samples. So we see that this is a big data set, 27 samples, almost 7,000 grains. Most of these samples have between 250 and 300 analyses. So they're a really nice, rich data set. And one thing I noticed when working with this is that there's one analysis that has an error listed as 0 MA. And that actually causes errors if you try to plot PDPs. So I'm just going to filter out that one analysis and redo it. So you'll see if you compare the 2 plots, we have one less analysis, and that's gonna prevent the error. You could go back in and make that a small number like 0.1 or 0.05 or something like that. But just for simplicity, I'm going to just filter it out. All right, so there's 3 ways you can plot these data that I've pre-given you. You can plot all the samples listed in stratigraphic order. You can plot all of them as a single group, or you can plot them into these different age groups that I've predefined. So I'll just do this top one first. And I'm just going to run the code and let's see what we get. Taking a minute or two because this is a lot of data. All right. So that's what it looks like. It's a really long plot because there's so many samples. And if you like what you have, you can run this code to save it. So basically open up a little dialog box prompting you to save it. So there was a question about that. And here it is as a PDF. Full vector, you can edit this in Illustrator or whatever. So in the last 15 minutes, what I would like you to do is to go up in here, first pick which group you want, or you can define something yourself, and then try modifying these parameters to make the plot look better than this. And then if you like what you have, you can go click on that link and paste like a snipping shot of what you have into the shared Google file. And there's a place to put, why you chose the parameters that you did. That's optional, but if you want to share that, that's fine. And then the last few minutes, we'll sort of loop back together and see what you guys came up with. So any questions about that? All right, feel free to plot away and just give a shout if there's any questions.
Hey, Glenn, there were some people who had some issues setting things up right at the beginning. Could you make us a breakout room so we can help folks individually with that?
Yes, I will try. Add a room. Okay, it looks like it automatically made a room 2 with me and 3 other people. So I'm not sure why I did that.
Hopefully those are the 3 people who wanted to go into that room.
Yeah, so if you would like to go into a breakout room, could you post in the chat, and I will try to add you to a breakout room with me in it. Okay.
Are you seeing those chats come up, Glenn?
Yes, I am. I am seeing
Okay.
them. I'm trying to take care of that.
If you want to pass control to me, if you want to make me the host, I can
Okay.
sort of moderate a
You
little
can do
bit.
this. Okay.
And then I'll give you a little bit more freedom to help out.
I will gladly give you control. Right. Host. Okay. You should be host. Feel free to send me to a room with the folks that indicated some help.
Joel, somebody else wanted to do a breakout room with plotting their own data. I can try to show them how to do that in Drive if you want to put us into something. It looks like Isaac and I can help out with that too.
Yeah. Okay, let's see. All right, so you should have been invited to join a room.
Is that room 2?
Room 2 will be individual data.
Okay, I'm going to kick Glenn out of that one.
All right, kick him into room 1.
Yeah.
Joel, which breakout room is for the Google Colab help?
Should be room 1.
Room 1, okay.
Can you get-
It says I've been assigned to room 2.
Yeah, let me see if I can move you.
I went there and they asked that I leave, so. Okay.
Yeah, they didn't want you around anymore. So I am trying to get everyone where they need to go. If I'm not getting you where you need to go, please send me a chat. So for the people that are still here in the main room, let me know if you're having issues. I can try and help. I'm not as familiar with Python as Glenn and Sam are, but I will do my best to answer questions if there are any.
Hi, yeah, I had another question. Is there a way to only color the lines instead of like the entire area underneath the KDE?
you're saying like the vertical bars behind the KDEs?
Here, do you want me just to share my screen so I can, it might be
Sure.
easier. Okay.
Are you able to? Forget if I've allowed that or not.
No, I think you'll have to enable it if that's possible.
It's probably possible somehow.
I think there should be like a little arrow button right next to the share screen and then just say like multiple participants can share screen.
Yeah, unfortunately not.
Oh, okay.
You're right.
No problem.
I suppose I could make you a co-host, and that should allow you to share the screen.
Okay.
Let's try that.
Yes. Okay. Can you see this?
Yeah.
Okay. It's just okay. So is there a way to just color these lines instead of shading the area underneath the distribution?
Oh, yes, I think so. Just looking for.
That's a very particular thing, so I don't know if it's possible.
I feel like it should be. Trying an example here. Yeah, blast.
I feel like it's a situation where you might have to add a line of code just because it is kind of a particular request.
I think you're probably right. It seems like it should be a fairly easy fix, though. Again, I'm not as familiar with Python as I am in MATLAB.
Yeah, no
I'm
problem.
looking for the code that might do that, but yeah, I'm not sure. You might have to ask Glenn or Sam that. Again, I think it's probably a fairly simple fix or a fairly simple bit of code, but I'm not familiar enough to answer that question, unfortunately.
Okay, yeah, no problem. All right. Well,
Haley,
thank you so much.
how did you set your to get your nice line graph with the peaks shown? What did you change in the original code?
Oh, like to get them stacked on top of each other?
Yes.
Yeah, so I changed the very top line of code to both.
Ah, okay. Thank
Yeah.
you.
Yeah, of course.
Ryan, what part of the code are you at? Are you down at the bottom working on like the Bloom et al. Data set?
Yeah, so I'm in the Bloom et al. Data set, and I've loaded all the data and trying to plot both the CDF and the KDE plots.
Okay.
So I reloaded it, and it didn't seem to change the results. So
Yeah.
still trying to play around with it here.
So you set what to plot as both, and then you're trying to plot both the relative and cumulative functions.
Yes. So it shows it plots the relative function, and it draws a box for the cumulative thing, but there's no lines in it.
Yeah. Nuts. I got an error as well, just by changing that.
I ran into the same error. Did you change when you go down to the cumulative distribution options? Did you say plot CDF as true? Because if you go up to the very top into what to plot and put both, and then don't change down below to true,
Yeah.
it'll give you that error.
Right. Yep.
That makes sense.
That's probably
Thanks.
it.
Joel, I just want to ask you a general question about the recordings. Will these be uploaded to the short course drive?
We will distribute them. I'm not sure exactly how we will distribute them yet. I need to talk to Jennifer, the short course coordinator, to see what their preferred mode for distributing them is. If they don't have a preference, then yeah, we'll probably upload them to the drive.
Okay, great. Thank you.
Yep.
Joe, did we talk about how to load our data into this, or we have to pretty much download Python and then work with that if we want to deal with our data?
No, you should be able to upload your data to Google Colab.
How to do that?
Glenn, do you want to address that?
Oh, how you import your own data?
That's
Yes.
right.
Yes. So I'll just say that I'm new to Google Colab. I haven't been using it much before, but the way to do it is you have to have a Google Drive account.
Mm-hmm.
You have to put your data into Google Drive,
Mm-hmm.
and then you right-click your data file, and then I think you go to properties, or I'd have to refresh my memory, but you can basically get this ID number that's a string of letters and numbers. And that's what I put in the Google Colab file to actually load the data. So in that first cell all the way at the bottom, there are those two Excel files that each have those long IDs. Now, if you're using Python not through Google Colab, you can load data just by pointing to its address on your machine, or if it's in the same folder, you just sort of give it the file name. And
Okay.
so that's what I normally do. But for Google
Okay.
Colab, the only way I know how to do it is through Google Drive.
Do we have to name do we have to put in the specific format, or just basically like line 16 is showing, it should be good enough?
Yeah, so your data has to be formatted in a certain way, and you should be able to get access to the presentation I showed. Also, if you go on, if you search for GitHub detritalPy, it'll take you to a web page that gives instructions, and there's also a manual. So,
Okay.
and I think there should be a link in the Google Colab folder itself. So I'd recommend visiting the GitHub page. That will give you some instructions and in terms about how to format your data. You do have to do some data organization to use detritalPy. It's maybe not quite as convenient as just copy pasting data into Excel or something like that, but the goal is that you do that once, you make this nice data table, and then you can just, you don't have to do it again.
Okay.
Glenn,
thank
I had
you.
gotten a question that I didn't know the answer to. Will detritalPy handle no data rows in your Excel spreadsheet okay?
So currently it does not. I would like to change that. And so if you have a row that has no data or string or anything but a number for the age and error column, it will return an error. But I would like to make it more flexible so it won't. Ultimately, those will need to be filtered out before you try to feed it into something. But yeah, so you kind of have to clean up your data. If you have analyses that you want to discard, you should take them out. Otherwise, they'll be plotted. In the future, I think that it can be a little bit more sophisticated than that, but currently that's how it is.
Glenn, I asked Joel this, but I'm not sure if you have an idea. Is there a line of code that allows you to only color the lines on your KDE instead of coloring the entire area of the distribution below the line?
So no, the lines, the actual lines on the KDE will always be black. But if you wanted to color them, you could import them into Illustrator and color them as you like.
Okay.
It could be possible to add that feature. It's just something I haven't coded in yet. So, but yeah.
All right. Thank you.
Mm-hmm. Well, Joel, I know we're a few minutes over, and I don't want to cut into people's lunch too much. I know there were some issues getting Colab to run. So I'm not sure how many. There are a couple of figures that have been shared that I could show the group.
Yeah, why don't you do that? We've got about 5 more minutes. Planning on sort of breaking here at noon Eastern time, so 9 o'clock Pacific, and wherever
Okay.
you are in between. So you've got about 5 more minutes, and
Okay,
then we'll take about half an hour break after that.
Okay. Okay. Great.
Yeah, why don't you go ahead and share what people have worked on, and
Okay.
that might be a good way to prompt some questions.
Yeah. If you wouldn't mind making me host or enabling screen share, I can go on from here.
And I dive in with one quick question.
Sure.
Okay. Hi. So I've tried changing the x-axis and I've cut it off at 1,500.
Mm-hmm.
Is there a way to now renormalize the CDF so that it reaches 1 in the space of my new short x-axis?
Yeah. The way to do that would be to filter your data. So actually remove the older ages, because otherwise it will always use all of your ages in the CDF. Yeah.
Cool.
So if you really don't want to see or plot or care about those old ages, you can just filter them out.
Awesome. Thanks.
Mm-hmm.
So I made you a co-host, Glenn. Are you able to?
I am. I can
share your screen. Okay, cool.
Yeah, I'll go ahead and do that. Okay. We have some participants have shared their screens, which is great. And so I'll just go through and we can look at some of these. So this first one, you can see that they chose to, so I showed a plot that just stacked all the samples on top of each other, and they were in separate subplots, and it was a huge file, very tall. This person has used the group by formation option, and so there are these different groups, and now it fits on the screen, and you can sort of see it better. So I think that's improved over the plot that I showed initially, for sure. So here's one where they've used that same option of plotting by age instead of everything, and they've added some color coding, and you can see that it looks like they've used the default colors that I had been using earlier. So of course you could change the colors if you so wanted to, but they've also expanded it a lot. They made the plot a lot wider to help visualize sort of the detail, so that can sort of help you see some of the detail on the young end and some of the detail on the old end. All right, so this person chose to plot everything as a cumulative age distribution. So again, we're looking at the sample groups divided by age, and as Kurt mentioned, I agree. I think looking at the data in CDF space can be really useful. It might not be quite as intuitive in terms of the peak heights, but in terms of characterizing the data set and looking at a lot of samples together, it can sometimes be pretty nice. So you can kind of tell that the samples share, have some similarities, but they're sort of these end members. Like there's a pink end member down here and a purple one up here. It's actually interesting that the modern Brahmaputra and the modern Ganges sort of form envelopes on this. So we'll talk about mixture modeling later, but you might begin to wonder if these different deposits from the fan could be different mixtures of those two rivers. And that wasn't quite as apparent in the other plots, but looking at it in CDF space, you can really see that. So I think that's a nice way of doing it. So in this plot, they've chose to use the heat map function, which you can see what it looks like in this data set. And they also have the, and I'm not sure if these are PDPs or KDEs. The spikiness down here makes me think they're probably PDPs, and the PDPs are colored, so you can sort of see the different colors there. These heat maps are almost like barcodes. It's sort of can help visualize things. So for example, the Brahmaputra has a lot in this young category, and that shows up in some of the fan, but not the oldest deposits. The oldest deposits, the barcode looks a little bit more like the Ganges. And so things are definitely changing in this data set. All right, here's one where they show both the CDF and the KDEs, and they color the KDEs according to age. They've changed some of the colors that I had initially. So instead of that sort of, I think I used saddle brown for old ages, they've chosen a pink color for the old ages. So here's a plot that shows, again, the groups. It seems like most of these plots have chosen to look at the groups colored according to underneath the age distribution. And I'm not sure if these are, I think they're plotting a KDE just based on how rounded these distributions are. Note that the colors here match, so like that green matches that green, and that's sort of intentional, so you can easily match them up. So this one plots the age peaks, which is nice. So you can sort of compare here. That one's 522. It's actually a little bit older than some of these other ones, so that's sort of nice. This one's sort of similar to one of the other ones we saw. Again, pretty simple, but it kind of gets the message across.
Can I dive in with another question there?
Sure.
So how do you change the color coding that's shown here, where it's like a different color per sample?
Yeah,
and not
so
the color by age.
Currently, I picked a set of colors to use, and there's not a way of changing that in the code. So if you want this to be purple instead of green, I think that could be something I could add, but it's not currently implemented. And by the way, if there are things that like that you think, hey, that'd be neat, just send me an email, and I've got a running list of detritalPy improvements that I'm always chipping away at. So, but yes, you can always change it in Illustrator too. So if you go into a software, you could select the green and make it purple or whatnot.
Cool, thanks.
So I like this one because they're applying two distributions, the KDE and the PDP, and the PDP is colored according to these age groups. They've chosen different colors, and they've zoomed in on the younger side of the plot, so they're not showing the older ages. Okay, so this one uses the vertical bars and it looks like they've used some transparency to make them not so, so saturated. Cool. So this one, there's an option for plotting an uncertainty envelope based on, and I'd have to refresh my memory on the paper and the procedure, but I think it's outlined in the manual. So the idea is that these are uncertainty envelopes associated with these cumulative distributions. They've used that option. They plotted the peaks. It looks like they have a very permissive peak definition. So they're including basically every little bump as a peak. You could, of course, change the parameters to filter some of those out if you wanted. Good. So this one is cutting off the young ages. So they're only looking at the older ages. They've chosen their own colors. It's good. And this one is a heat map plot. And I've got some notes here. Kept with relative because it's easy to compare the peaks. They try different XDiff, and XDiff is the number that you discretize the x-axis. So that means that there's a probability point every million years, and that's usually an appropriate amount of points for most data sets. So I think that's a good default. But this shows the heat map pretty nicely. So that's good. So I think we're out of time, but thank you all for making some nice custom plots. Hopefully you've seen that there's lots of ways that you can plot detrital age distributions, and there's probably not always a right and wrong way to do it. A lot of times you have to consider your own data set and try to make decisions that communicate the data like they should be. At least that's my view. But a lot of nice plots made here just in a few minutes. So thanks.